Okay, for the second part of our lesson, we're going to look at a very similar problem from the very next year, number 6 from 2015. Here we've got a Maclaurin series. You just need to remember that that means that the center is at 0. That's all that means. And that's evident if you look at this. You're not subtracting anything from x, so centered at 0. So it's given by this function. It also gives you the first 3 terms and the general term. And it tells you that it converges to f of x as long as you're within the radius of convergence, which is denoted by the capital R. So just like the last question, the first thing is to find that radius of convergence. And they even give you a little hint to use the ratio test to do that. So let's do that. The ratio test tells us to do the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term. So when we look at our terms, we can ignore the fact that 3 is negative because of the absolute value. So we could just treat this as 3 to the n minus 1 plus 1, or 3 to the n, times x to the n plus 1 divided by n plus 1 times the reciprocal of this, which would be n, over 3 to the n minus 1 times x to the n. Simplifying a little bit, 3 to the n divided by 3 to the n minus 1 would just give us 3 in the numerator. And similarly, x to the n minus 1 divided by x to the n would just give us x in the numerator. And then we've got n over n plus 1. And since this is a limit as n is going to infinity, n over n plus 1 is just 1. So that gives us the absolute value of 3x. And according to the ratio test, in order to converge, that must be less than 1. Therefore, the absolute value of x must be less than 1/3. And that gives us our value for r. The radius must be 1/3. So that's part A. Let me now duplicate this slide, and we'll look at the next part. Part B and C kind of go together here. All right, so part B. Write the first 4 non-zero terms of the Maclaurin series for f prime. We need the first 4 terms, and if you look, we're given the first 3 terms of f. So this n equals 1, n equals 2, n equals 3. So we're going to need the 4th term. So let's go ahead and just find that. If n equals 4, we'll have negative 3 to the 3rd. That would be negative 27. And then we would have divided by 4, negative 27 fourths, times x to the 4th. So this would be the 4th term. We've got the first term, second term, third term, and now we got the 4th term. And we're just going to take the derivative of those 4 terms. So f prime is approximated by these 4 terms. The derivative of x is 1. The derivative here, multiplied by 2, negative 3x. The derivative of 3x cubed is 9x squared. And then the derivative of our 4th term, if you bring that 4 down, the 4's cancel, you just have negative 27 x to the 3rd. So write the first 4 non-zero terms for the Maclaurin series of f prime. Here they are. And then express f prime as a rational function for absolute value of x is less than r. So this is kind of a tricky wording of this. But the idea here, it's the same as in the last example that we looked at, which is that f prime is just going to be equal to the sum of a geometric series. If we can analyze these terms and recognize this is geometric and figure out what the ratio is, then we can use the sum of a geometric series to write this function. So what are we multiplying by each time? Obviously, we're multiplying by negative 3 each time, and we're also multiplying by x. So r equals negative 3x, right? 1 times negative 3x, negative 3x, multiplied by negative 3x again, positive 9x squared, and so on. So we recognize that ratio, and then we know the first term and the ratio, so we have everything we need. 1 over 1 minus negative 3x, or 1 over 1 plus 3x. So this is kind of tricky because it's only when we see that result that we recognize, oh yeah, this is a rational function, right? Kind of like a fraction type function. But you maybe wouldn't know maybe what to look for with that wording. But if you are familiar with these problems, you can see it's the same strategy that they used in the last year, just a different wording. Okay, now let's do part C. Okay, so part C, we take a detour here. We've been dealing with this f of x, and then all of a sudden they're like, write the first 4 non-zero terms of the Maclaurin series for ex. Like, what does that have to do with anything? But, okay, I mean, we can do that. So the Maclaurin series for any function, remember we'd centered at 0, and so the Taylor formula with x equals 0 would be like f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the 1 plus f double prime of 0 over 2 factorial times x to the 2 plus f triple prime of 0 over 3 factorial times x to the third, and so on. And so we want the first 4 non-zero terms. So as long as this first term isn't 0, then that will make 4. And so let's do that for e to the x. So f of 0 would be e to the 0. 0 factorial is just 1, and x to the 0 is just 1. And e to the 0 is also 1. So our first term is just 1. What's nice about e to the x is that its own derivative. So f prime of 0 is also 1, and f double prime of 0 is also 1, and f triple prime of 0 is also 1. All of these derivatives will be the same. So 1 divided by 1 times x to the first is just x. 1 divided by 2 times x squared. So how about 1 half x squared? And then 1 over 3 factorial, that's 1/6 x cubed. So write the first 4 non-zero terms of the Maclaurin series for e to the x. E to the x is approximately equal to these 4 terms. Now, use the Maclaurin series for e to the x to write the third degree Taylor polynomial for g of x, which is equal to e to the x times f of x at that same center. So g of x is going to be approximately equal to the product of these terms that we just found, 1 plus x plus 1 half x squared plus 1/6 x cubed, and so on, times the terms for f of x, which if we look back at the top, we've at least got the first 3, x minus 3 halves x squared plus 3x cubed. And we did find the fourth term earlier, although I don't think we need it in this case. And so we want to find the third degree Taylor polynomial here, which means we need to multiply these together, which is like a distributive property idea, but we'll only keep terms up to degree 3. So let's do that. Let's distribute the 1. We'll have 1 times x, 1 times negative 3 halves x squared, and 1 times 3x cubed, and we'll keep all those. So x minus 3 halves x squared plus 3x cubed. Okay, and next we'll distribute the x. So we'll do x times x and x times negative 3 halves x squared. That'll give us x times x is x squared, x times negative 3 halves x squared, negative 3 halves x cubed. And we'll stop there. We don't need to, the next term would be a degree 4, and that's beyond what we're looking at right now. Now let's look at our next term, 1 half x squared, and we can distribute that onto the x. So plus 1 half x cubed. And again, we'll stop there because we've reached the highest degree that we're interested in. So then once we combine these terms, we'll have g of x. G of x is approximated by, let's see what kind of terms we got here. We've got just x. We've got some x squared terms. Negative 3 halves x squared, 3x squared, and Sorry, that should be 3x cubed. So we've got these two x squared terms, negative 3 halves x squared plus 1x squared. So that leaves us negative 1/2 x squared. So that's our next term. And then we can look at our x cubed terms. 3x cubed minus 3 halves x cubed plus 1/2 x cubed. So negative 3 halves plus 1/2 is just negative 1. 3 minus 1 is 2. So plus 2x cubed. And so on. So those are the first three terms, and that's what it asks for. So very strange problem, but there it is.